My goal has been from the beginning is to just try to share knowledge that people have with the public so that we can all kind of get a little more resilient to the changes that are happening around us. I want to thank the library for hosting me these past few years. Before that, I was at the Northshire Bookstore. You might have seen me there. I also want to thank GNAT. Mike's on the camera tonight, so thanks GNAT for recording this for those people who couldn't make it. I did want to say that, you know, my first kind of exposure to building science was through the Building Science Corporation. This is a book that came out in about 2004. Has a lot of good information. It's written by Joe Stiebrook. The L is silent. But I take classes from him almost every year still. I just took one last week just on roofs. So it's 8 hours just talking about building science of roofs. So the classes can be pretty deep and extensive, and I'm trying to keep this presentation from going there. So if I don't really get deep into things, please excuse me, but we could spend weeks on this. So I'm trying to make it understandable and efficient. So besides the Building Science Corporation, I'm a member of SEON, which is the Sustainable Outreach Network, Sustainable Energy Outreach Network. They're over in Brattleboro, and I'm part of a building science guild there. It's a group of builders and architects and engineers, and we all get together once a month and kind of try to share knowledge with each other and try to bring up any issues that we're trying to solve, and we all kind of brainstorm and work together to try to collaborate. Also subscribe to Green Building Advisor, Building Green. Those are now online publications. Before that, it was Environmental Building News back in the late 90s and early 2000s. All good sources of reference if you'd like to learn more. Anybody see last month's issue of Vermont Magazine by any chance? If you go to the very last article, my wife Nancy is in the back, and my house is featured in there. So if you want to take a peek into how we live and learn more about our 800 square foot house, you can do so there. Also, if you want to learn more, there are videos on GNAT that I mentioned before. If you go to their search and just type in sustainable, a bunch of them come up. Also, I have mostly product and technique videos on YouTube. I have about almost 30 different videos on different topics and products, mostly regarding energy efficiency, cutting edge technology, and that kind of stuff. So we're going to ease into this a little bit. For the last 26 years, I've been keeping a journal. This is like a garden journal is what it's called. And each book is 10 years, so there's 10 years of information here. I've been doing it for 26 years. And it's always good to kind of look back and see what happened, you know, on a typical November 16th, what would the weather be like, et cetera. It's amazing how often things repeat themselves. No matter what the weather's doing, we'll see the first thing on the same day every year. So that's one of the most interesting things that I've come across. We keep track of the temperature, the weather, sightings in the yard, harvests, et cetera. So if you opened up randomly to a page, that's what it would look like. So there's 10 years on each page, and it's just by the date. So we're actually on November 16th. And looking back to November 16th in the past 26 years, I've had a high temperature of 66, a low temperature of 19. Usually it's around 50 degrees. A lot of years we've had periods of weather that have been above 50 degrees for 2 or 3 weeks, right around this time of year. So we're a little bit chilly. But we were a little bit warm last month, so it's making up for it. We've usually had some measurable snow. We really haven't gotten that this year. Some years we've had as much as like 8 inches of snow that has fallen by now. Most years it's just 2 or 3. So we're a little behind in that. In our yard, we usually have a hairy woodpecker that visits this time of year and pecks on our barn for whatever reason, looking for grubs. And we usually have dandelions blooming in the lawn, and we have these pink violets out in the cottage garden that think this is spring again or something, and they usually bloom at this time. So don't be surprised if you see a dandelion blooming in the grass next week. Over the last month, I was able to go to one of Frank Lloyd Wright's houses that he designed over in Manchester, New Hampshire, the Zimmerman House. We also summited a Camel's Hump for the first time last month. And now that we set the clocks ahead and we hadn't had a hard frost, last week I was still harvesting raspberries in the dark with my headlamp on. But we just cut them down this past weekend, but we were still getting raspberries right up till last week. So what's the purpose of a house? Shelter, right? So it keeps out the elements. It keeps a comfortable temperature, comfortable humidity, keeps out the wind, the rain, the heat, the cold. So in it's hard to see this, but that's the edge of the building right there, that red line. So in a good design, you'll have overhangs, and any rain that comes down will be pushed away from the house and then follow the grade away from the house, not pitched towards the house. But you don't have to look very far down the road to see a building like this with no overhangs, grade trim right down to the grade, so they have siding right on the ground. We do get snow here. And then you'll see things like this, where there's no overhangs, there's rotting clapboards. Down at the bottom where the rain and snow is always hitting, wicks up moisture, so we have rotting wood. And besides that, they had some issues with their window flashing details. So very expensive new building, not too long ago. One of the things that we have to control is airflow, wind especially. If it's a cold, windy night and you have cracks and leaks in your house, you can feel it. You don't have to have a door or a window open. It'll blow right through the walls. So there's a few ways we can control this. It's kind of this white stuff. It's hard to see here. But we'll often see something like this. More recently, they've added a little bit of a rain screen to it so that these are little bumps on the stuff, so it allows the water to fall through. And then this is more recently, this is actually a fully adhered membrane, which we'll talk about a little bit more later. But this is the weather resistive barrier. We refer to it as a WRB, but that's what keeps the wind out, keeps the bulk rain out, and it also helps control moisture flow. So it'll be vapor flow in and outside of your walls. We've got samples of some of that stuff coming around. So when we look at an existing house that somebody's renovating and they wonder why they have rot in their walls, and we find the plywood here and then the clapboard there and nothing in between, it's not very surprising that they're getting rot in their walls. The old standby that was used still pretty recently is tar paper, 30-pound felt, 60-pound felt. Back then, it used to be the weight of it, so it used to literally be 30-pound or 60-pound. But now it's number 30 and number 60. They actually switched where the number sign is. So it used to stand for pounds, but now it just stands for number. So it's not the same quality that it used to be. But the advantage of this stuff is it actually, as the plywood or the sheathing behind it gets wetter, it actually has pores that mimic pores that open up and allow moisture through, so it'll actually dry better when the substrate's wet, and it'll do the opposite. If it's raining, it'll keep the bulk water out. So it's been a pretty good product. We actually used it as recently as, this is probably 4 years ago. Client decided that's what they wanted to use. It was before this stuff was residentially available. They did have fun with all their nails there that you can see. But again, tar paper is one of the options. This is, then the scientists got involved, the chemists and the corporations got together, and they came up with different kinds of house wrap. I went through a few of them. The concerns we have with this is you can see, like, here's one layer and then another layer, and wind and things, wind-driven rain can actually get up inside there. So there's actually openings. The way this is attached, if you look carefully, you can see there's actually staples every foot or so that are holding this on. So you're putting up something to keep out the wind and the rain, and then you're putting holes in it, right? So it kind of defeats the purpose. It's not all over, but it does happen. So not necessarily the best system. So we started looking for something better. This was put out by Sega. It's called MyVest. And the advantages of it is that it had taped seams. So you would tape it all together so it would all be sealed. It was self-healing, so if you put a nail or a cap nail or something to hold it in place, it would seal itself around those penetrations. You could also flash it easily to doors and window openings. And its vapor permeability can vary, again, like the tar paper. When it gets moister on one side than the other, the pores can open up. So it was a really good product. We used this 3 or 4 years ago on this project. Since then, something better has come out. So this is do we have a sample of the blue skin? Okay. So this product is peel and stick. So now you don't have to put any nails through it. You don't have to use staples to put it up. You don't have to tape it together at the seams. It's all in one. It's vapor permeable. It's self-healing. So any penetrations that you do put it through, it seals. So it's pretty much all of those things in one product, and you don't need the tape. You can use this as tape right on itself. So this is Blue Skin. It's put out by Henry is the manufacturer. Yeah. And still, if you get really anal about penetrations, you can have all kinds of sealing systems. So this is kind of that same blue type material, and it actually has these rubber gasketed holes. So if you're running wires or pipes or something through the exterior wall, this is a good way to seal those. They have them also for vent stacks for plumbing chases, etc. So that's all part of the system. So the other thing that we really have to keep out here in Vermont is the cold. There's all kinds of insulation, just like all kinds of weather-resistant barriers. We have spray foams, we have rigid foams. So spray foam is kind of hard and chunky. We have extruded polystyrene. We have polyisocyanurate, but all those are basically chemical foams that get combined together, expand. They have some kind of trapped gas, and that gives you the R value. There's also a different kind of spray foam. This is isonine, so it's a open cell spray foam instead of a closed cell, so it's not as high R value, it's not as rigid, it's less expensive, it's lighter weight, but it does not air seal completely, and it does not vapor seal completely. This is our favorite insulation. This is dense packed cellulose. So to put that on the walls, they kind of put up a netting on the walls and on the ceiling They put up a netting that's stapled carefully to all the insides of the studs, and then they blow it in with a hose, usually one at the top, one at the bottom. So you can see these little holes here, and some under the windows. And that's where they blow it in. They blow it into a high density so that it cannot settle. So it's actually denser inside those walls than if you ground it up and let it settle over time. So that's called dense packed cellulose. It's a recycled newspaper. And then we even have clients that use straw bales for insulation. So not the easiest thing to work with, pretty affordable. Some of the challenges we had were with the air sealing details, having to put all kinds of gaskets and flanges on, especially behind a timber frame, to make it a continuous air and weather barrier. More recently, not only do we put insulation on the inside, we also put insulation on the exterior, and I'll explain why in a minute. But this is a rigid board insulation on the exterior. You may have seen either this or this used on the exterior in the past. Both of these burn pretty well, and we have friends who are firefighters. So we've actually gone to this. This is a pretty dense, packed rock wool. It's slightly compressible, but it's a rigid board. It's mostly recycled content. It's, I think it's slag and then minerals that are whipped up like cotton candy and then laid out into, onto a table and then compressed with a press to make the rigid boards and then cut the size. So if we're looking at the parts of a wall, we can do it there or we can do it here. So we have our siding on the exterior. The purpose of the siding is not just to make a house look pretty, it is to keep the rain out as much as possible. But you'll see, there's a gap between all the clapboards, so when there's a wind-driven rain or something like that, there's an opportunity for water to get behind here. That's not a concern. That's why the second layer of defense is strapping, so that creates this void here. So any rain that gets through the clapboards falls down in this open cavity, down to the bottom and drains out. The next line of defense is this exterior insulation, depending on what's used. This drains quite well. The Roxul board, it's semi-hydrophobic, so because it's glass-like and it's made with oils, water doesn't really like going through it or staying in it, so it will drain and dry relatively quickly. The next line of defense, your final line of defense is way back here, and that's your weather-resistive barrier. This is the peel and stick version. So rain would have to get through here, not fall down here, get through all this insulation, and still would have to get past this, which it really can't do.
And the blue skin is lets vapor out?
Yes, yep, vapor permeable. So it doesn't allow bulk water. So if you look at the size of water vapor and compare it to the size of a water droplet, water droplets like the size of a basketball, and water vapors, more like the size of a little bit bigger than a marble, So it has pores that are small enough that a basketball can't fit through, but if you have vapor inside your wall that's trying to escape, the pores are big enough to allow something that small to get out. Good question. So then, beyond that, we have our studs, typically 2x6 wall, and this is where you would fill with dense packed cellulose or fiberglass, or they actually have a spray-in dense pack fiberglass now. And then there's dry spray cellulose, there's damp spray cellulose. There's actually a Roxul type product that can go in bats. So there's a lot of insulations. There's probably more insulations than any other option in a building. Then you have your rigid foams that we talked about earlier as well. So if you take a chainsaw and you cut right through the middle of this wall, it looks something like that. That doesn't have any exterior insulation on it, but a simple wall back in the day, it was sheetrock on the inside, insulation in the cavity, some kind of sheathing, usually plywood here. Then this is the strapping, the rain screens just inside the strapping, and then outside is your clapboards. So the most important things about building science to remember are these three things. Hot goes to cold, wet goes to dry, and high pressure goes to low pressure. So it's all about the earth is always trying to be in equilibrium, right? So if something is really wet, it's trying to dry out. If something is really hot, it's trying to, hot air always flows to cold air. And if there's a real high pressure, it's trying to release that pressure through a lower pressure. So those are the big three principles. So if it's hot, humid, wet, and high pressure outside, what time of the year is that? Summertime, right? And then on the inside, it could be cold if we have air conditioning. It's definitely cooler than it is outside, especially drier if we have air conditioning. And we can have a lower pressure depending on what our fans and things are doing in the house. So we could have all of those conditions driving water vapor, humidity, etc., into our house. The good news in Vermont is on a bad year, that's about 3 months, right? June, July, August are usually our hottest 3 months. This year, we had maybe 3 weeks that somebody might have tried to use their air conditioner this summer, right? Sometimes we have warmer days in the end of May, the beginning of June, and then early September than we do all summer. I think this year was a good example of that. So even though it is vapor driving in, it's not freezing on the way through, which is something we don't have to worry about in summer. And it's a small percentage of the year. On the other hand, when it's cold and dry and low pressure outside, and hot and wet and high pressure inside, the vapor drive is going in the opposite direction. So let's say you're taking a hot shower in a bathroom, and you get out and the mirror is all steamed up. So that mirror being steamed up is showing you that it was hotter in the room, there was a lot of moisture in the air, and it was condensing on a colder surface. We'll get into condensation soon. So when does this happen? Wintertime, right? Especially in bathrooms, kitchens, any commercial buildings that have, dishwashing, etc. In Vermont, how many months of the year are we heating our house? Right? I guessed about 7. I've actually saw people the last week of September lighting their first wood fire this year. No, it was the last week of August, right? We had a cold snap. It was like in the high 40s, low 50s. I think it was the last day of August. There were actually people posting that they were lighting up their wood stove. Normally it's, part of October, most of November, December, January, February, March, April. Sometimes it can sneak into May. It really depends on the year. But that's 1, 2, 3, 4, 5, 6, 7 out of 12 months versus 3 out of 12. So a much higher percentage. So building science can be this confusing if we let it. This is called the Psychometric Chart. And it has graphs. It's basically grafting. This is temperature here. So 35 degrees way down here, 120 degrees Fahrenheit way up here. And then this is humidity, relative humidity. So 10%, 20%, 30%, 40%, 50%, 60%, 70%, 90, 80, 90, and that's 100% relative humidity there. So it's basically correlation between humidity and temperature. And to give you an idea of where we live, this is the human winter comfort zone in red, and this is the human summer comfort zone in blue. So that's where we're always trying to get our buildings to be, somewhere between 80% humid and 20% humid is the least we could handle, which is a pretty wide range. But we're always in this, you know, this looks like 78 degrees, 77 degrees. In the summer we can handle, and in the winter it's closer to 67 for a low. So somewhere between 67 and 77 degrees, and mostly we like it here in the, you know, 60 to 30% relative humidity. That's the majority of this. So that's what your house is trying to be all the time, is right in that little sweet spot. Unfortunately, the Earth is, sometimes it's over here, sometimes it's over here, sometimes it's over here, sometimes it's over here. So we're always trying to change what's outside as it's coming through our walls to our house. So I'm going to simplify that chart a little bit. So if you have, this is actually this side, if you have 75-degree air outside at 50% humidity, if you cool it 15 degrees, it's actually 18 degrees, but I rounded off, it'll go from 50% humidity to 100% humidity. So just cooling it that much. So the reason for that is hot air can handle a lot more moisture than cool air can. So it just has to do with how many particles there are bouncing around, how much moisture they can hold. But that's the simplest way. So cooling something 18 degrees can double the humidity. And when you get beyond 100% humidity, you get condensation. So if it's more than 70 degrees outside and less than 60 degrees inside in your air conditioning, somewhere along the way there's condensation happening, whether it's in the wall, outside of the wall, could be on your windows. To look at that graphically back at this crazy chart, here's, what is this? This is 80 degrees, and this is 60 degrees, and we're cooling it. So it's going from 50% humidity, okay, this is 75 degrees right there, 75 degrees. We're cooling it to 60 degrees. So to use this chart, you just follow it across. You're going from, this line is 50% humidity, and you can see right there it's at 100% humidity if you move that straight across. So graphically, that's what that chart's telling you, same as that. Moving over 15 degrees, doubling the percentage of humidity. And that's what you get, right? So if something is hot and humid, it hits something that's cold, it condenses, and that's when we get liquid water inside your wall. So even though, right, you can't see any water flying around out here, it's not a rainy day, it's a sunny day, but somehow there's all this moisture on the outside of the bottle. It's not coming from inside the bottle out. The beer is not sweating, right? This is actually all the humidity getting cooled more than 15 degrees and turning into liquid water. So going the other way, if we have outside air that's 35 degrees and 90% relative humidity, and we heat it up to 70 degrees, it cuts the humidity by a third. So you'll often hear people saying, you know, that their wood stove is a dry heat. Well, it's because when you take in 90% humid air, even though it's at 35 degrees, it's 90% humid. That's, a lot of our winters are more humid than you would expect. But you're bringing it into your house, right? And when you heat it up, it dries it indirectly because the warm air can hold a whole lot more humidity than the cold air could. So looking at the chart, we're starting over here, 35 degrees, going up to 65 degrees, and it's going from a 90% humid there to 30% humid there. So there's that straight line. So it's not the wood stove that's drying out the air, it's the temperature change. So it's going from being 35 degrees outside at 90% humidity. So it's very humid. If that was summertime and it was 90% humidity, you'd say, boy, it's really wet outside. But in the wintertime, 90% humidity isn't really much, because inside that's only 30% humid air at 70 degrees. Make sense? So another way to look at it, this is a little simpler than the psychometric chart. So this is kind of a graph I drew. These are the months of the year. So winter is kind of in this half right here, what's going to turn out to be the wet half. And this is more of the more milder temperatures. So here's August is kind of at this peak, and mid-January is at the bottom here. So this is, if I have a wall assembly and I try different types of insulation on the inside, on the outside, some on the inside, none on the outside, all on the outside, what happens with that? So if you look at this top line way up here, that's 4 inches of insulation on the exterior. What this is showing is, this is that dew point at 35% relative humidity that we were talking about at 40 degrees. This is when you can get condensation in your wall. Anything below this line. So if we had almost like this, no insulation in your wall and all insulation on the outside, like this, then you'd have almost no chance ever of getting any condensation in the wall. But who doesn't want to put some insulation in here? You're building it out of wood, you might as well fill it with something. So that's the safest way, and they do this. I met with an architect that was I'm trying to remember, I think they were in like New Mexico or something like that, designing buildings, commercial buildings, and they just do exterior only insulation. And that's all they put. And they never have to worry about condensation in the walls. They use steel studs out there, so condensation in the walls means rusting. For us, it's more of rotting, but for them, it's rusting. So that's how they build their walls out there. And then these are all varieties of some insulation. So if you start down here, this is 2x6 wall with no exterior insulation. Then we move up. So this is the most potential. This is saying pretty much all winter you're getting water in your walls. And then as you move up, this is some exterior insulation, 1 inch, 1.5 inches, 2 inch, etc. So the more exterior insulation you have, so actually a 2x4 wall with just 3.5 inches of insulation and exterior insulation is actually has less chance of condensing than a 2x6 wall filled with insulation, because the higher the ratio of exterior to interior, to summarize, the less chance you're going to have of condensation. So 100% outside, 0% chance of condensation. If you have, twice as much outside as you do inside, you have nearly no chance for condensation. If you have the same amount inside and outside, you have a little bit of chance for condensation, a pretty good chance. If you had no insulation outside and all insulation inside the wall, then you're definitely going to get condensation. Yes? So the question was, exterior insulation is a relatively new thing. And my answer was that yes, probably within the last 15 years, exterior insulation in America, exterior insulation has been kind of a new thing. The Canadians have probably been doing this for 25, 30 years, maybe 40 years. But they have a colder climate than we do. But when you're looking at old houses, there's a whole different thing, right? They don't have necessarily air tightness. They don't necessarily have, certain products in their walls. They might have fiberglass that moisture can fly right through. They might not have plywood on the exterior. They might have boards with gaps in between them. So the advantage of an old house, if you don't mind wasting a lot of money or heat, is that the walls would dry very quickly in the winter, because all of the heat is just flying out the walls and it's bringing all the moisture with it. So you never really have to worry about condensation in the walls of an old house. If you were to take an old house, which I've seen happening around town, and then put something with like a foil-faced polyiso or some insulation that has a foil face on it, then you're stopping all of that moisture. It hits the foil. We'll get into this a little bit, but foil is a metal, right? So water can't go through metal. Easiest way to look at it. So when you have 1 inch of foil face on an old house that's leaky and drafty and has fiberglass in the walls, suddenly you're actually making a situation that was working just fine because we were losing all that heat. You're making it become a problem because now you're trapping that moisture in the wall. And that's when you'll start to see rotting, paint peeling, et cetera. Yes? Yes, so the question was, can you limit how much moisture escapes your house and gets into the wall in the first place? It's pretty much to summarize, right? So for many, many years, the code was that you had to put polyethylene, right? This stuff on the inside of your walls, which if it was continuous and there were no holes in it, it would be fine. But who doesn't have an outlet in their wall or a light switch, right? So you put all this perfect plastic everywhere or a window, and you cut a hole through it and you run wires through it, and guess where all the moisture goes? It's going to go for, you know, the path of least resistance. It's going to travel right along those outlet boxes, the light switches, et cetera, and you're going to get the condensation in the walls, and then the plastic here is going to keep it from drying to the inside. We are getting a little ahead of ourselves, but good question. So again, this is the worst case I saw with nothing on the exterior to slow vapor or the rain or the wind. But this is an old house, as was mentioned. And you can see right here, 16 inches on center. You can see these paint stripes. So that's, to me, that's saying where the studs were, the vapor wasn't going through the wall. And where the studs aren't, so here's paint on the outside, but there's no paint here, and then there's paint on the outside. So the moisture is just flying right through between the studs and literally blowing the paint right off. So you can see that's gap there, gap there, gap there. So that's where I can say, well, they've got a vapor drive issue. Again, it's an old house, so it makes sense. The vapor drive was flying through the walls and peeling the paint. Here's another example of this. This is a house on Route 30. They have air conditioning, but you can see the studs right here, right? So this is some kind of cedar siding, I think, but you can see all this mildew on the exterior, and you can see right where the studs are, so you know that the moisture is coming through between the studs. So there's probably not good vapor control either on the inside or in the middle of the wall. They probably don't have any kind of rain screen that I would guess. But I would hate to see inside this wall. Actually, I'd like to see it. But if I was the homeowner, that would be a telltale sign for me that something bad is happening inside. So there's definitely moisture going through that wall. And this is what can happen, right? You can get rot. And then when we have moist wood, that attracts carpenter ants. Carpenter ants typically only eat moist wood. So you go from, you know, just a little bit of moisture in the wall, a little bit of rot, and then it becomes carpenter ants, and then they start eating the house, you know, and then it just kind of snowballs. So it can be a pretty big deal. So now, of course, it's not simple. It's not just one material, and they can all handle moisture and vapor and airflow the same. They're all made out of something different. So this is similar to this wall. This is actually looking through a window. You can see out here they have some kind of strapping. Here they have this foil-faced polyiso. That's right in this section here. Then they have plywood here. And then this is a window opening, so it's 2x6 for a window, but there's probably going to be cellulose or some other insulation here. So all of these materials have different properties. So it's not just temperature that can control condensation. It's not just change in relative humidity or pressure. It's also how vapor permeable each of these materials are. Here's a quick and easy chart to look at, but you know, wood siding's about 10 perms, brick veneers 40 perms, asphalt paper about 30 perms, house wraps, the range is from 5 to 50 perms. OSB sheathing is one of the least permeable sheathings you can have, 2 perms. Plywood is a little better at 10 perms. And then you get into the things that are, so the lower the number, the less permeable they are. And when you get down here to like foil faced, because it's a sheet of metal, right? Less than or equal to 0.1, 0.1. So that's saying it's a vapor barrier. There's no water getting through that. It's called vapor impermeable. So, you know, this is kind of a scale going from vapor open to vapor closed. So just like glass, a perm rating of less than 1. So just like glass, foil, etc., when warm, moist air hits that, it's going to condense. So that adds to the issue. So if we have hot, wet, high pressure, cold, dry, low pressure, you know, the vapor drive is coming in. If we happen to have polyethylene, this was code for years, polyethylene on the inside of your walls. During the summertime, if you had air conditioning, it would be condensing on the exterior side of this poly. So you'd actually getting liquid water on the outside face of this. So the question was, you know, a house built with this system, which we did for about 50 years, poly on the inside, you know, how concerned are we that it's going to rot over time? Is moisture really going to build up? The easy answer is it's not usually a problem. If the house isn't air conditioned to, you know, 30 degrees, you know, if it's not in Florida, and every once in a while you have a dry day during the summertime, so that's what I'm showing here is slowly this will dry back out. When the temperatures drop at night, when the humidity drops on certain, you know, sunny days, then you get some drying. And again, it's a very small portion of our year, so you might have 5 to 10 days of serious vapor drive, and then you might have 30 or 50 days of slow vapor trickling out. So we've been fortunate over time that our walls, even built with this stuff, have been able to dry out. But when you get into the 7 months of the year, when you've got the heating going, and you have something with foil on the exterior, right? That's a little bit different condition. So you've got, especially in a bathroom, hot, wet, high pressure, all that's going out, it's hitting the foil. It can't get through the foil, no matter what. Doesn't matter if there's 10 feet of insulation on the exterior, it's still gonna hit the foil and potentially condense. And that will drip, they'll condense and drip inside the wall. Again, slowly, you know, fortunately we don't take showers 24 hours a day. We take showers for 20 minutes and that's it, you know. So then eventually that'll dry to the inside, it'll dry through the sheetrock, and over time, you know, it can dry out. Again, bathroom's probably the worst case scenario for this. The worst thing that we can have is wintertime inside, cold outside, hot and wet inside, electrical box, polyethylene on the inside, and then something on the exterior. Could be vinyl siding, could be, you know, a half-inch, they sell this in half-inch sheets, could be a half-inch of this. So then what happens is you've got that, all that vapor drive going out and around the electrical box, all that condensation is building up because it's hitting this exterior. We thought we controlled it from the interior, but we have a double wall basically, and moisture cannot dry in either direction. And we've seen houses that the, you know, bottoms of the studs were rotted, you know, right through. And this is why, because they had a double vapor barrier with, again, outlets, light switches, anything, a light sconce, any penetration that you can think of going through a wall. So that's the worst case scenario. So back to the simpler times, we used to have walls that looked like this, right? You know, it was 2x4 wall, fiberglass, sheetrock, strapping. These are the walls I'm dealing with. Okay, so this is, we have board and batten siding, we have horizontal strapping, we have house wrap, then we have boards on the exterior, we have cellulose insulation, then we have straw bales, and then we have timber frame inside that with plaster, earthen plaster. So this is actually one of our projects. So trying to figure out where we're going to run into trouble, if we're going to run into trouble, how we're going to avoid trouble in something like this gets a little more complicated. Fortunately, we don't do one of these every year. But wouldn't it be great if we could find a wall system that no matter where the condensation happened, we didn't have to worry about it. We had very little condensation. It could dry in either direction. It could dry to the inside. It could dry to the outside. They call it kind of like a vapor open wall. So no matter where the moisture is, it's not concerned about that. It can dry in either direction. And that's what we've been developing probably for the last 4 years, 3 years now. So we have this is an example of it. So this is probably 2 years, two versions back. We've actually improved this, but cellulose in the wall cavity. Cellulose is vapor open, it's like 75 perm. Plywood is 10 perm, so that's kind of your throttle. That'll slow things down so they don't just fly through. And then this house wrap is closer to 40 perm. So you're going from 70, 10, 40, and this stuff is vapor open. Don't remember off the top of my head, it might be 60 perm, something like that. And then right out to the strapping here and out. So very vapor permeable in both directions. This will keep all the bulk water out. So we're not having condensation. I mean, we can have a little bit of condensation, but we're not having bulk water getting through any of this. So whether it's summertime and the air conditioner's on and the vapor is going this way, or it's wintertime and the heat's on and the vapor's going that way, it can dry in either direction. The cellulose actually works like a sponge. Cellulose can handle a lot of moisture. And if there's happens to be a wet spot because there's an electrical outlet or something there where most of the moisture is concentrating because it'll go to wherever there's an easy out. So if it goes behind an outlet box or something like that, the cellulose might get damp in one spot, and what it does, it'll wick. It's just like a sponge, it'll wick moisture in all directions because it's going from wet to dry. And then, the sheetrock and things can allow it to dry to the inside, but if the vapor drive all winter is staying in that direction, all of these things will allow moisture to get out, vapor to get out. So in section, it kind of looks like this: cellulose here, plywood here, 4 inches of exterior insulation, strapping, and then your siding and stuff. So the first project we did, I had gone to Joe Stiebruck's classes, and I learned everything I thought I could. And I took lots of notes, so both of these notebooks are full, so it's like 80 pages of notes from class. And I came up with this wall system, and at the time, this fully adhered membrane wasn't available on the market. It was a commercial product, but they still didn't sell it as a residential product. So this was the next best thing. This was a vapor permeable, all taped, weather-resistant barrier. So we put that on, and then outside of that, we put on our Roxel, and then outside of that, we put the strapping. So again, multi-layers. If the rain gets through here, it can drain down between the strapping. If it gets through the insulation, it hits this and drains out. And again, it breathes in both directions, so the clapboard's on the outside. You can't really tell the difference between this house and a house that has no exterior insulation, a house that has fiberglass in the walls. Looks the same, right? So it works better. So after the project was finished and after I spent months trying to convince the builder to trust me and the client to trust me that this was going to be a system that worked, Building Science came out with an article in January of 2016 that said flow through assemblies. It's a Building Science Insight, number 91. You can actually go to the website and read it. But they call it the more perfect wall. Because they had come up with a saying like 5 or 10 years ago, the perfect wall, you know, this is how a wall should be. And they had a vapor barrier in the middle, and it had to dry to the inside or to the outside. But they soon showed that this was even better than that because it could dry in either direction without having to worry about condensation happening in between. So with the clients behind me and the builder behind me, and then Building Science behind me, I said, okay, this is the wall system we're going to use for all of our projects. So later that year, we built this. This is a multi-purpose barn. We built this house, which is the client's just moving in this week. We're renovating our barn to be our office. So one of our barns, our barn in our backyard, we're turning into our office. We stripped everything off, right back to the plywood. We put the blue skin, we're putting the Roxil. And more recently, a new product has come out. I'll pass this around. Yeah, it's called Thermal Buck. So you can see this big chunky thing out here. So if we have all this insulation and this strapping, if we have all, 3 or 4 inches of insulation and then 1 inch of strapping outside, that makes our windows, you don't want your windows to be behind all of this. You have to flash the windows out here. So we had to develop something that would push the windows out to be flush with the siding. And this was made out of a combination of plywood, 2x4s, and the blue foam XPS. So those 3 products, and then all wrapped, right, with some kind of tape, or in this case, the blue skin. So it was, I think there were 9 different steps to build this. What that does is it's pretty much all of this and the buck. So you just sit that inside the window opening, and it comes out the thickness that you need it to be to handle the thickness of the insulation and the strapping. It's all one product. You just glue the corners, basically, you caulk it together, and it automatically has a weather-resistive barrier on it. So it's almost like a rhino liner, a bed liner for a pickup truck. That's the outside coating. And then the core of it is made out of a high density EPS, so extruded polystyrene, expanded polystyrene, sorry. So that's what that is. It's very strong, it's waterproof, it's insulated. It's got the ones we use are 4-inch, and it's R14, which is higher than this insulation. And the guy who designed it was a builder in Pennsylvania, and he came to our house, and he helped us install the first 6 windows. But he not only invented it because he was a builder and felt like he needed it, but he had it, designed and manufactured, and now we can use it on our products. And we did a little video with him on the installation process. But it's one product, you just have to cut it and caulk it together, and it's done, instead of 9 steps and plywood, foam, tape, and 2x4s that we used to have to make it out of. Yes. Yes, so that costs more, but if you use that, and if you tried to do this and that at the same time, it comes out to, RK Miles did some actual tests with their employees to build this and to build that, and it actually came out to a savings, mostly because of the huge savings in labor. So that's way faster than this, probably, an hour per window faster. It's amazing how much faster that is. And that more than makes up for the increase in cost. So it's actually a cost savings if you add the materials and the time together. Good question. What about condensation on this product? Because it's vapor impermeable, The good news is it's just this wide and it's around the windows. So your window, the glass of your window is vapor impermeable, right? So it's like making your window 4 inches bigger is all it really does. So all of this is already vapor impermeable. It's a little bit more vapor impermeable, but all of the wall cavity is still vapor permeable. So even if this is on the outside, moisture can get around it through all the other cavities on the inside. Good question. So here's a combination of blueskin and thermal buck being installed. This is another project. This is number 4 of these. And then this will be number 5. This is going to be an affordable house, 600 square foot affordable house. And we're going to use the same system. And again, it's all because it works and we don't have to worry about it. And it's proven. So the question was, do you have any experience with the foam expanding or any concerns, or can you see that and cracking the outer layer? So you can hit the outer layer with a hammer and it will not break through the outer layer. That's how it's flexible, yet it's very resistive. And the foam is at a very dense, it's a very dense foam. The inventor actually drives his pickup truck on one of these pieces to show how strong it is and how dense the foam is. It's the foam that's in this is actually used for road beds. It's a filler for under road beds, so that's how dense it is. It's not like this stuff, you know, it's much more dense than this. So I don't have any concerns with it. So the question was, you know, doing this may be best practice, but it sounds like it's expensive. And how do you do that for affordable housing? And that is certainly a challenge that we're facing with this project. But what we're trying to do is we're going to continue to see if there are other ways to make it more affordable. You know, somebody actually at a presentation last night brought up the fact that if this stuff is so, you know, water repellent and waterproof, do you even need this stuff, you know? So there are things that people are looking at, you know, whether or not we can do something different with the strapping, how much insulation we can get away with. Again, you could go to, with this system, you could actually go to fiberglass bats on the inside, which would save something. You would lose some of that ability to control moisture in the wall. But so the question is, you know, basically, you know, these are more expensive to use up front if you're building a house today, but long term, doesn't that kind of pay for itself because you don't have to do the repairs? You don't, you know, if you don't have a rotted wall and you don't have to replace a rotted wall, you know, that's good long-term durability. The same thing goes with a lot of the heating systems we use. We use, you know, air source heat pumps or ground source heat pumps, more expensive up front than putting in an oil boiler, but it's going to save you, you know, a lot of money in the long term. So the question is, you know, does this compress this insulation? Roxul is not as firm as, you know, some of these foam boards are, so it does compress some, but going to, in this case, a 5/4 or a 1 inch thick piece of wood, that's not going to flex at all when you screw it in, so it's all going to compress equally. Again, the first projects we did, we actually, as they were screwing in the strapping, they just held the level in the other hand and made sure it was all plumb. I've come up with another system since then that we used on our barn and we used on one of those houses that you saw where we actually put golf tees in here, right? So golf tee cut exactly to the thickness of the insulation. So you poke it through the insulation, it bottoms out at the face of the plywood, it holds the strapping, it can't compress at all, and then you just screw above and below the golf tee, and that keeps us at exactly 3 or 4 inches. So I haven't patented it yet, but it's part of the system. Yep, so so the question is in like a modular construction, you know, if it's a house that's built in a factory setting, can they build it from the inside out? And that's what they do. So what happens there is they actually put up the sheetrock and they put the outlet boxes in the sheetrock. And then because they're working from the inside out, they can stand outside the house and spray foam around all of those outlet openings before they insulate. So do tight houses need air exchange? Always. Every single project we do, even our barn conversion to our office, which is only 250 square feet. We have a fresh air, it's a heat recovery ventilator. So it's bringing in fresh air, but it's heating it with the outgoing stale air. So they're exchanging the heat. So instead of bringing in 30-degree air, we're bringing in 70-degree or 60-degree air because it's crossing the exhaust and preheating the air on the way through. Right, so what if you could design a house that had no penetrations, no water pipes, electrical wires, no chimneys, no sewer ventilation, all that. Everybody strives to do that. The closest that we've gotten so far is this guy. So you see no overhangs, right? The thing that I said never to do. But that's just so that we can get our continuous air barrier right up and over in all directions, right? So we wrap this box in this blue skin, and now what we're gonna do is we're actually gonna attach overhangs on the outside. So that way, and those are self-healing holes that we're gonna be screwing through. So that way, all of this is going to be continuously air going out. Sometimes, depending on what heat, a lot of times I use ground source heat pumps, so you don't have to have penetrations that way. So what we'll do is, a lot of times is we'll have a ceiling, and then we'll have the insulation up above that so that we can, so the roof is insulated, and the ceiling area, anything above that, we can run ducts and wires and stuff, and it's still within the building envelope and it's not penetrating anywhere. Other times we'll actually create ductwork chases. So we have a project right now where it's a ground source heat pump, which some people call geothermal, but it uses ducts, big rectangular ducts, not the ones that quack, but the ones that are rectangular and tubular to get the heating and the cooling around the space. That can be a challenge. So we're actually disguising it as cabinetry, so we'll have cabinets below it and cabinets above it and the ducts running through the middle, and it's just going to be paneled on the outside. But you have to get creative on how to keep from penetrating anywhere and move those things around. And we usually have 2 or 3 chases going from the basement to the second floor so that they can run pipes and electrical stuff vertically without penetrating the envelope. Right. So we usually have chase right above the utility room, for instance. Excellent. Well, thanks everybody for coming out. If you want to stop by and ask me more questions, feel free. Hopefully you learned something.